So let's take a look at the general linear model. I think you're a bit tired of statistical diagrams, so I put my cats here, Sigmund and Catharsis, because we know that statistics is easier when we have cats, and also general linear model is a very important type of modeling. That's why I would like you to associate it with something nice, because you're probably going to use it in your research at some point or other. But what is general linear model? Basically, it's a way of writing different regression models that can use a mixture of different variable types. So a general linear model is basically a common approach to estimate multiple regression models, ANOVAs, analysis of variance of different types. And we will explore a little bit those types of analysis of variance. And there are also extensions of general linear model. For example, generalized linear model for non-normal distributions, or for some weird variables like logistic regression and other types of functions that can link predictor and outcome. It's not necessarily a linear function. And there are also linear mixed models that we'll explore a very little bit today. If you're interested in practicing general linear model, by the way, there is a nice website with lots of experimental data for practice. And today we will explore three instances of general linear model, three different models within the framework of general linear model, using as an example one dataset that I was working with last week. It was a French study conducted by my colleagues where they compared the efficacy of three different counseling interventions aimed to help people abstain from alcohol. This approach is called motivational interviewing, and they used three slightly different motivational interviewing protocols to see which one is more effective. And it was a randomized design with pre-test and post-test. There were three groups of patients. Unfortunately, those groups are very small. Altogether in the study, they had 34 individuals, and we can ask a question, can we get any good results with just 34 individuals? And we'll see the answer very soon. I only took two dependent variables here: alcohol abstinence self-efficacy, which is basically a self-evaluation. Do I believe that I can abstain from drinking in different situations, like when my friend offers me a drink, or when I just want to raise my mood? And the second scale, which we use as dependent variable, is Rosenberg self-esteem scale, which is an important indicator of well-being. So we measured those variables before people went through this counseling course and after. And we wanted to see whether there was any effect. So the data for this study looked pretty much like this. AAC at its abstinence self-efficacy, time 1 before, time 2 after, and Rosenberg self-esteem scale, time 1 before, time 2 after. So as you can see, the number of observations is very small. Luckily, the number of people per group is the same. But otherwise, we would have been in big trouble with such a small sample. But as you can see, the means are fairly different. So self-efficacy increases almost by 1 standard deviation, and self-esteem increases almost by 1 standard deviation in all groups. So the effects are very strong. The question is, what do you compare with what? Do you compare groups at pre-tests, or do you compare groups at post-tests? Or do you compare pre-test with post-tests in each group? And in principle, you can do it. But there are more optimal ways to analyze this kind of data using general linear model. For a pre-test, post-test dataset, there are basically three options that you can use. The first option, the simplest option, is basically a t-test or a one-way analysis of variance. You calculate difference scores. Basically, for each person, for each variable, you calculate the difference between the post-test and the pre-test, and the result is called a difference score. And then you can compare these different scores across groups to see if the change was the same or not the same in all groups. This is a very easy approach. If you don't have much time and you don't have any other options, it's also a possible approach. Unfortunately, it has some drawbacks. They are reviewed in this paper by Dimitri van Rumriel, which you can easily find, so I will not discuss those details. The second approach, which is also commonly used, is called mixed ANOVA, when you model group as a between group variable and time as a within group variable. And the third approach, which is a little bit tricky, is ANCOVA or regression approach, where you model post-test as your dependent variable, and as a covariate or predictor, you use your pre-test score and group. And we will try to analyze this data using these three models and see what comes out. So first, one-way ANOVA. For alcohol abstinence self-efficacy and for Rosenberg self-esteem, I have calculated difference scores using the SPSS transform compute function. So I just computed new variables. And then I take these two difference score variables and I include them into one-way ANOVA. And SPSS gives me some results. Basically, there are two portions. First, the ANOVA table, which tells us if the difference between the three groups is statistically significant for each variable. So if you remember, we separate our total variance into within group variance and between group variance, and the proportion of variance that is between group is called eta squared, and we evaluate statistically the significance of this proportion of variance, and as a result we get this level of significance. So we can see that the differences in alcohol abstinence self-efficacy are statistically significant, which suggests that some program maybe works better than some other program. However, for Rosenberg self-esteem scale, this significance level is not very good. It's 0.059. So we cannot really confidently conclude that there are differences between the groups. And then we can take a look at effect sizes. Luckily for us, the version 27 of SPSS has started giving a normal bunch of effect sizes. Before it was just eta squared, and it was kind of mislabeled in some analysis, also in some versions. But now we have, in addition to eta squared, we have epsilon squared and omega squared. What is the difference between eta squared and epsilon or omega squared? Eta squared kind of assumes that your sample is your general population. And in small samples, the variance can be underestimated. So eta squared, as a result, can overestimate the size of your true effect compared to general population. So if we tested this effect in a larger sample, our eta squared would have probably become smaller. So it's exaggerated in very small samples. That's why people have proposed other effect size estimators, epsilon squared and omega squared, which make adjustments which correct for small samples. The interpretation is still exactly the same. It's a proportion of variance that can be attributed to an effect, to differences between the groups on this predictor, on this nominal variable. And for omega squared, you see that it's 13% of variance in the outcome that is explained by group membership rather than 19. And this difference is so large because it's a small sample. In a large sample, eta squared and omega squared will be pretty much the same. Usually people are not so familiar with omega squared. And now we're interested which group has higher scores and which group has lower scores. In SPSS we can request some plots. Unfortunately, in one-way ANOVA they are still fairly useless because they contain no confidence intervals. So you cannot be sure whether this difference is large or small. You don't see what to compare it with. But, well, at least something. And you can request multiple comparisons post hoc or post hoc tests. Basically pairwise comparisons between each group and each group. And because sample is very small, I just requested LSD, least significant differences, not what you're thinking about. Least significant differences, which is a post hoc test that doesn't make any adjustment for multiple comparisons, because already my sample is so small, my power is so weak, I don't want to cut it further. And you can see that the difference between group 1 and group 3 is statistically significant. And of course, they are on the opposite ends of this graph. And the difference between group 2 and group 1 and 3 is not significant. So group 2 is somewhere in the middle. Although it's closer to group 1 than group 3. And here, this difference is 0.06, kind of. Yeah, and this is the same way you can interpret the second graph. So it looks like the intervention was more successful to help people abstain from alcohol in the third group. But with respect to self-esteem, we cannot really be confident. The overall effect is not significant, and for post-hoc test, it's only the difference between group 1 and group 2 that is significant, but the picture is not so clear. So this is one-way ANOVA, the simplest way to deal with pre-test, post-test design. Another type of analysis that can, one-way ANOVA can be conducted through compare means menu or through general linear model menu. If you have more than one independent variable, or if you have at least one repeated measures variable, the only place you can go in SPSS is general linear model repeated measures. So what is mixed ANOVA? Basically, we treat this experimental design as a mixed design, where we have one between group variable and one within group variable. And this within group variable is the difference between pre-test and post-test. It's the effect of time, which will capture the difference between pre-test and post-test in all groups. So when we set this model up, what do we need to do? First of all, we need to set up a repeated measures factor. We give it a name. We take how many. We tell SPSS how many levels we have. Here we have 2, and we press add and define. If you have several within subjects variables, you can include several. And then this next window appears when we can assign our variables, the columns in our data matrix, to different levels of this within subjects factor. So we say which is pre-test and which is post-test. And our between subjects factor is still group. And we can also request SPSS to make us a nice graph. So what are we looking for when we are conducting this analysis? The group factor is normally not very useful to us, because these are the differences between the groups when all time points are taken together. So if we kind of average together pre-test and post-test, the group factor will separate groups, which is not what we want. So we just ignore it. The time factor. Captures the difference between pre-test and post-test in all groups pulled together. If you have an experimental group and a control group, it makes no sense, because you don't want to pull together experimental and control group. You want to separate them, because you are expecting that the change is different. However, here we had 3 intervention groups, and here time factor kind of quantifies was the intervention effective or not. And what we are really looking for is the interaction between time and group. This interaction will tell us that the change from pretest to posttest is not the same across groups. So essentially, it will tell us what the difference score analysis has told us. The only tricky point about mixed ANOVAs is that when you have more than one independent variable, either between group or within group, instead of eta squared, you get another measure of effect size, which is called partial eta squared. Of course, standard eta squared you can still also get, but it's not as informative. Eta squared is a proportion of total variance that is explained by a particular effect. However, the exact amount of this proportion will depend on how many other effects are in your model. That's why usually people prefer a version of eta that is called partial eta squared, where first we separate the variance of dependent variable into portions that are associated with different effects. So here in the denominator, instead of the total effect, we only have the sum of square for the error term associated with this particular effect. That's why eta squared partial can be interpreted as the strength of our effect relative to error. And it's kind of more informative. If you are interested in more details, there is a nice link that you can follow, which explains everything. And there are also omega squared and epsilon squared. And then G power, there is coins F squared. So don't confuse them. But there are plenty of materials on that. So let's take a look at our results. Here now we are only interested in those two factors, the effect of time and the interaction between time and group. So I did not include the group effect to avoid overburdening this presentation. And for alcohol abstinence self-efficacy, we see that the effect of time is significant and it's actually very strong. The partial eta squared is 0.61, so there is very little error left. And the interaction between time and group is also statistically significant, and the strength of this interaction is like 0.19. So it's a fairly strong effect still. However, do those numbers look familiar? I think they do, because they are exactly the same as the ones we got when we conducted one-way ANOVA using different scores. So if you are doing a mixed ANOVA, this interaction effect will be exactly the same as what you get just based on different scores. So why conduct mixed ANOVA then? Well, because it also might give you additional information about other factors, or sometimes you have several independent variables, and then in one-way ANOVA it's not possible to model them. That's why. But in principle, if you just have one between group and one within group variable, of course you can just use different score approach easily enough. And for Rosenberg self-esteem scale, we also still get the same result. It's still not significant, and the partial eta squared is still 0.19. But the effect of time is also very strong, even stronger than for alcohol abstinence self-efficacy, suggesting that those who stopped drinking as a result of this intervention, they also boosted their self-esteem. And we can ask SPSS to give us some plots. In the version 27 in general linear model, the plots look a little bit nicer. At least you can make a little bit of sense of them because they have confidence intervals now. However, the problem is that they overlap. So these plots are a little bit less ugly and a little bit more informative, but still they are not very useful. Just compare the plots produced by Jamovi for the same data, for the same analysis. Don't they look nicer? That's why if you want to publish your plots, probably just take Jamovi, don't take SPSS. Yeah, so from these plots we can see that for alcohol abstinence self-efficacy, there is a good increase from pre-test to post-test, and this increase is strongest in group 3. However, for Rosenberg self-esteem, there is also some increase from pre-test to post-test, but it's not so clear. It's definitely weaker in group 1. It looks like weaker, but we cannot really be so sure because the differences between the groups are not so pronounced. So if you are facing this situation, if you are really interested in the difference between these 3 interventions, what can you do? Well, there is a solution. If you are having a problem with a very small sample, for example in your master's dissertation with a pre-test post-test design, your solution that can really help you is called ANCOVA, Analysis of Covariance. It is also a variant of general linear model. What is ANCOVA? It's basically ANOVA with a letter C, ANOVA with covariates. What is a covariate? It's basically an additional interval predictor. So you conduct your ANOVA just in a normal way, but you also add another interval predictor. What do you gain by doing it? You take out the variance associated with this interval predictor. And if this interval predictor explains some error variance, it explains some other sources of differences in the scores on your dependent variable, then your experimental effect has only to explain, is calculated as a proportion of remaining variance. So the total variance becomes smaller. The amount of error, you take out some error from your variance box, and what is left may not obscure your effect so strongly. So your effect will be stronger on this background of smaller error variance. Essentially, ANCOVA is equivalent to multiple regression. So we could do exactly the same thing in multiple regression by dummy coding group membership. However, ANCOVA is a little bit more conveniently done in SPSS in terms of plots and so on. So you don't get these nice plots and you don't get these flexible post hocs in regression. So when do we want to use ANCOVA? When we want to control for alternative explanations, or we want to exclude other sources of error variance. For example, you're testing an educational intervention. Obviously, you want to control for IQ, or you're interested in in how students of different disciplines study. Probably you want to control for their school graduation exam scores. So some pre-existing individual differences that contribute to your outcome variable picture. So ideally, this number of covariants should be very small, and they should be correlated with the dependent variable, but ideally they should be independent from each other. So you cannot really include many covariates. It's best to include very few, especially in small samples. You don't have much statistical power. So in this situation, more than one covariate would not work. Another important thing about covariates is that it must be completely independent of your experimental treatment. So if you are, for example, testing effects of an educational program, your IQ scores should be measured before your educational program began. Otherwise, they might reflect some effects of your intervention. And if you take out this part, you actually take out some effect variance instead of error variance. And as a result, your effect gets weaker. And another assumption of ANCOVA is that the slope of association of covariate with your dependent variable is the same across all groups. Again, in ANCOVA, you have no more, you don't have the flexibility. And this increases your statistical power. In regression, you can potentially model different slopes by including interactions, just as we did last time. But if you don't include interactions in regression, it will be exactly the same as ANCOVA, because they are both essentially general linear model. So in our case, with a pre-test, post-test design, why is ANCOVA beneficial? Because there are individual differences. For example, in alcohol use self-efficacy, in self-esteem, there are pre-existing individual differences. We can exclude them from our post-test measurement of our dependent variable. So we can control for pre-existing individual differences. That's why our covariate in this case is our pre-test score. And our fixed factor is our group. And our dependent variable is our post-test score. And you can use this approach even if your design is not fully randomized, even if these groups are even if these are existing groups, if it's a quasi-experiment. Because you have pretest, you can control it as a covariate, and as a result, your estimate of your experimental effect will be good, will be unbiased. So we go to ANCOVA, analyze general linear model univariate in SPSS, and we set this thing up. So first, we get this table, which is now called test of between subjects effects, because we don't have repeated measures here. We have them logically, but we don't have them technically. Technically, this is considered as a covariate. And we see that the effect of this covariate is statistically significant. Well, of course, it's supposed to be. So there were some pre-existing individual differences in the belief that I can stop drinking, or belief that I can refuse a glass of wine when it's offered by a friend. And at post-test, these pre-existing individual differences still remain to some extent. They are not very strong. A partial eta squared is only 0.17, so probably our intervention has changed these beliefs a lot, but to some extent these pre-existing differences still remain. But what's important for us here is this effect of group, which is statistically significant here, and the partial eta squared is 0.23. In our difference score analysis, our partial eta squared in mixed ANOVA, it was 0.19, so it has become a bit stronger because we have taken out some error variance associated with pre-existing individual differences. And what about self-esteem? Rosenberg self-esteem scale. Again, pre-existing differences in self-esteem, they explain a fairly large portion of variance. And that's quite logical because this intervention was not targeting self-esteem specifically. So people's self-esteem was not supposed to change as a result of intervention. However, group now is a significant predictor. Its p equals 0.048, and the partial eta squared is 0.21, slightly larger than 0.19 that we had because of reduced error variance thanks to taking out individual differences. And that's why it's now statistically significant. So we can publish it quite confidently. Unfortunately, for ANCOVA, SPSS does not give us any nice post hoc tests. However, what we can test here are planned contrasts, which are also essentially differences between the groups. And in this case, our group 1 was kind of treatment as usual approach, a minimum intervention. And we wanted to see if groups 2 and 3 are significantly better than group 1. And it's possible to compare groups in this manner. However, in principle, if you are very interested in comparing those groups, probably it's better to do this in regression framework. So then you just include your dependent variable post-test, predictor pre-test score, and dummy variables for groups. And then the effects for dummy variables will reflect differences between the groups. I don't know why in SPSS there are no post-hoc tests. In ANCOVA, it's a little bit strange because in Jamovi there are some. Yeah, but we can take a look at this picture of estimated marginal means, which are basically mean scores and groups, and it's the same picture. For alcohol abstinence, the group 3 was more efficient, more successful, and for self-esteem, both groups 2 and 3 are more successful. And in principle, if we compare them both with group 1, there are these marginal differences if this comparison was planned. So I hope you have got an idea of how we can use analysis of covariance. So it's another type of model. Of course, in the large general linear model and ANOVA family, there are several, many different types of models. Some of them we have explored in more detail, univariate models, mainly one-way ANOVA, factorial ANOVA, and ANCOVA. You are probably going to need at least one-way ANOVA at some point. But there are also repeated measures, which we have just explored. And another slightly tricky type of a general linear model analysis is called MANOVA, multivariate ANOVA. I'm not going to show you any examples of this because I don't really think it's very useful in most situations. But what is MANOVA? It is basically a situation when you have several dependent variables and you are interested in a cumulative effect of your intervention on this whole bunch of dependent variables. For example, each of these variables taken alone does not show any significant effect, but each of them captures a certain aspect of your experimental effect. And you want to see if altogether they capture the effect of your intervention. So if you have a situation like this, it might be a good idea to consider MANOVA. Some people think, okay, I have several dependent variables, and instead of doing several one-way ANOVA analysis, I will just do one MANOVA, and I will do it quicker. Unfortunately, it's much more complex. It's harder to interpret. It's harder to make sense of what's going on in your data. It also has some additional assumptions. It's not only homogeneity of variances, but it's also homogeneity of variance-covariance matrices and of regression for covariates. So it's a little bit more tricky. And also, when your dependent variables are either very correlated or completely uncorrelated, it has less power. The optimal situation for MANOVA is when your outcomes are kind of weakly to moderately correlated. So I'm not going to focus on MANOVA in detail because it's described in the book of Tabachnik and Fiedel quite well. So if you're interested in it, you'll know where to look. And we have explored three types of general linear model analysis: one-way ANOVA, mixed ANOVA, and ANCOVA approach. If you have a pre-test post-test design, the ANCOVA approach works best because it controls for individual differences. We have also explored a little bit the effect sizes. I hope you have understood the difference between eta squared and partial eta squared. The formulae are a bit different for between subjects and within subjects designs. So if you're interested in this formulae, you can take a look at this paper by Dan Lakens, where he also explains the tricky things. For example, the eta that is reported by SPSS is not quite the right eta that you need to enter into G-power. You need to make a little adjustment if you have a within subject design. And of course, I was positively surprised when I was preparing these examples that in SPSS now we have at least an attempt at decent plots, and we have at least an attempt at decent effect size tables, but unfortunately still there is not much flexibility. So if you're interested in GLM, perhaps Jamovi is the way to go. Okay, so we have explored a little bit general linear model, and as a little bonus track for today, we can explore a little bit linear mixed models and hierarchical linear models, but this is completely optional in the context of our course.